All right, so welcome back. Right now we'll be discussing the paper of Sarah Tate from I think the 1960s. Yeah, so what this says, so this paper, it says that we have an abelian variety over the fraction field of a DVR, and the theorem, or the first theorem, says when it has good reduction. So just some notation, it's much the same as before. Once again, we have R as a DVR, K as its fraction field. K sub S will denote a fixed separable closure of K, and we'll pick an extension to V bar of to the separable closure. Other things that we'll need, so we'll need the inertia group of V bar. It's just defined as the set of sigma in the absolute Galois group, such that sigma x is congruent to x modulo the maximal ideal of V bar, for all x in R V bar. And then we have the decomposition group as well, and this is just the set of elements in the Galois group that don't affect the evaluation V bar. We'll also need a few facts from number theory, so I'll just ramble them off really quickly. So first we have that if we take the decomposition group and mod out by the inertia group, this is isomorphic to the Galois group of K bar over K, where K bar is the algebraic closure of K, of small k. Yes, if we have an extension, so we have K contained in L, contained in K bar, so we have this. Then we have that L over K is unramified at V, if and only if L is fixed by the inertia group. And then finally, just a quick definition. So based on this being true, we'll say that if the Galois group of Ks over K acts on a set T, then we'll say that T is unramified at V. So this is a definition. It's unramified if IB acts trivial on V. Okay. Now, there's a few definitions that are used in the theorem, in the statement of the theorem. So I'll quickly give those. So first, we'll define a set of torsion points whose order divides M. So if M is prime to the characteristic of big K, then for an abelian variety, A over K, for an abelian variety, A over K, we define AM, A sub M, is defined to be the set of homomorphisms, group homomorphisms, from Z modulo MZ to the set of Ks rational points of our abelian variety. So this is the set of Ks rational points whose order divides M. Yes, and as a fact, so whenever A is an abelian variety, this is a fact, AM is a free Z mod MZ module of rank twice the dimension of A. All right, and the very last definition we need is called T sub L. And it's just the inverse limit of some phi's. All right, so the second definition, the last one, is we have L as prime. L is not equal to the characteristic of K. Then I'll define T sub L, A, where A is once again an abelian variety. So this is the inverse limit over all n of A, L to the n, which you can show fairly easily. This is a set of homomorphisms of QL modulo ZL to A KS. All right. So those are the requisite definitions. Now let me see the theorem. And the theorem, so the reason that this is relevant to Neron models is because the proof goes right through them. So A over K in abelian variety with K as before. We'll assume that the residue field is perfect. It turns out that this isn't a necessary assumption, but I think the proofs are more general then. And we'll have L prime, L's prime, and L is not equal to pair of K. Then what does the theorem state? It says that the following are equivalent. So first we have A has good reduction at B. Or at the close point of our DVR. This is equivalent to AM is unramified at B for all M prime to the characteristic of K. For all M prime to the characteristic of K, small k. Where, here I use the term unramified as in our definition up there. So B prime is very similar to B, but it says that there exists infinitely many such M, so there exists infinitely many M. As in B, for which AM is unramified at B. So it's just kind of, it's equivalent to B, but it seems a bit less strict, for which AM is unramified. And finally, TL A is unramified at B. All right, so we'll prove this, and the proof is, as I said, it goes through the Neron model, which is very relevant. And there's some nice corollaries to this. Note, for example, that part A of this theorem, or the A says that this part D is independent of the L that we choose. So this holds for all such L, for example. Okay, let's start with the proof. So first, let's note that for part C, so we can just use a limit argument. So by a limit argument, because TLA is defined as this inverse limit, C holds if and only if A L to the n is unramified at B for all n. All right. Now why is this nice? So this means that C implies B prime, because if C holds, then this part holds. A L to the n is unramified for all n. The n is infinite. So then we see from this that, well, first of all, B implies C, because if B holds, then certainly A L to the n is unramified, because L to the n is a subset of Z. And then I just said that C implies B prime. So already this is quite nice. And hence the proof now, it amounts to showing that A implies B, and that B prime implies A. So that is what we shall focus on. All right, so on to the part of A implies B. Let's assume now that A has good reduction. Capital A has good reduction at B. Well, so this, just by the definition of having good reduction, this means that, so this is the definition, there exists a smooth, proper model, which I'll somewhat suggestively call N. I mean, it doesn't have to be, but that's what we'll call it. Extending A to N over A over K to N over S. All right. So if we take N, so let's consider yes. So okay. So this is the definition. Now, but we also know that A over K is an abelian variety. So so let's consider the abelian, or consider I'll call it N prime for now. The Neron model of A over K, so N prime over S, is the Neron model of A over K. Then we know that N is now proper, or sorry, that N prime is now proper, so we can take N prime to be equal to N.
This needs an argument, right? So you can, one way to do this is to say that, so N is smooth, so the Neron mapping property of N prime gives you a map from N to N prime. And the image of this map is closed because N is proper, but it also contains the generic fiber, therefore the map is surjective. And now you have a surjective map from your proper N to your N prime, and then you can use the value of your criterion to check that N prime is itself proper. So we can indeed assume, so we can indeed deduce that N prime is proper.
Yes, okay.
I kind of anticipate this issue coming up, so I'm going to run.
Sure. Yes, okay, so we can assume, so because A has good reduction, we know, or it's not immediately obvious, but as David just said, we can say that N prime is proper over S, hence N prime is in fact an abelian scheme. Should I read out that argument, or?
Unless you plan to, but.
Sorry.
Unless you already plan to, but not from.
Okay.
As you, whatever you want.
Sure. In the interest of time, then we'll skip this. So yeah, this part's this is not immediately clear, but I mean it's not too much work it seems to show this. Okay. Conversely, if N, so conversely, if the Neron model is proper, then, I mean, the Neron model is already smooth by definition, so then we know that A has good reduction. So this implies that A has good reduction. Okay. So now, yes. So now we'll assume we'll keep to our assumption that we have the reduction, and we'll show part B, which is well, it's AM is unramified at B for all M prime to the characteristic of our residue field. All right. So what we need to show then, we need to show that AM is equal to the set AIM, where AIM, this is defined to be the the set of elements fixed by I, or the inertia group. Right, so part B says that AM is unramified, and just the definition of unramified says that it's fixed by ID. But for now, all we know is that we have a subset, so we have an inclusion in this direction. Right. So what we'll do, the way that we'll accomplish this, we shall show that AIM is a free Z mod MZ module of rank 2 dimension A. And that will imply this equality because we know, because A is an abelian variety, that AM is a free Z mod MZ module of rank 2 dimension A. Okay, so that's going to be our approach. And we'll do this by showing that AIM is isomorphic to a group.
You should also argue that, is it enough to you know that AO, the fixed elements by inertia is a submodule of it? Having the same rank, how does it imply that they are the same? You should say, well, if an element is not, if a multiple of a torsion element is fixed by inertia, then the element itself is fixed by inertia. Am I right? No.
So torsion element is fixed by inertia, then it's...
No, because every torsion element has a multiple which is fixed by inertia.
No.
So not right. No.
So sorry, I'm a bit confused. So if this is not... I mean, we have two finite groups that are both free Z mod M modules of the same rank.
Mm-hmm.
This is not... is there an additional argument to be made, or?
No, I don't understand why they have to be the same.
I see.
But, I mean, aren't they just like finite sets?
They just have the same number of elements.
They're finite sets with the same number of elements, one containing the other.
Yeah, indeed.
Okay.
So yes, which is isomorphic to the Z mod MZ to a free Z mod MZ module, which for now I'll call N tilde M of rank 2 dimension. All right, now what is this mysterious N tilde M going to be? Well, first I'll define N tilde. So I'll let N tilde be the special fiber of our Neron model. So I mean, N tilde is then equal to N base change over S with spec K. All right, that's just the definition of the generic fiber. Now, because N is an abelian scheme, we know that the special fiber is a commutative group over K. So N tilde is a commutative group over spec K. So we can define N tilde M in a similar way that we did for AM. Yes, so then we'll just define N tilde M to be the set of group homomorphisms from Z modulo MZ to N tilde N, N tilde K bar. All right, so it is the set of torsion elements of K bar rational points of the special fiber whose order divides N. All right.
So K bar is the separable closure? Or?
It is the algebraic closure in this case.
Yeah.
K is right.
K is what's right?
You did K is perfect at the beginning, so it doesn't matter.
Yes. Oh, that's right. Yeah, I guess that's where we lose perfectness here. All right. So as I mentioned, because n tilde is an abelian scheme, we have that, because n, so we know that n tilde is an abelian scheme, or abelian variety in this case, because n is, then this implies, by this fact that we have on this AM thing, that this is a free Z mod NZ module, of rank twice the dimension of the special fiber. But I mean, the special fiber in this case has the same dimension as A. So what we need to show now, okay, so this is good because now we have n tilde m. We know that its rank is twice the dimension of A. All we need to show now is that n tilde m is isomorphic to A I m. Okay. Yes. So lemma. We have an isomorphism of AI to the m onto n tilde m, and in fact this commutes with the action of the dv. Let's say that is the decomposition group. Yes. So commutes with the action of dv. All right, so how are we going to show this? Well, the proof of the lemma. Well, I'm going to define L to be the fixed field of the separable closure of the inertia group acting on the separable closure. All right, so this is in fact the largest unramified extension of K. Then what we have. So then the set of group homomorphisms from Z modulo MZ with AL, well, this is equal to this to the set of homomorphisms that are, or the set of IV homomorphisms from Z mod MZ to the separable closure. Right, it's just I mean, we're just saying that IV doesn't really act or acts trivially on these homomorphisms. But then this is just equal to A I to the M. All right. So if OL is the ring of integers of L, its residue field is K bar. This is a fact about the largest unramified extension, and it's because K is perfect in this case. So its residue field is K bar, and in particular, OL is a union of fatal extensions of R. All right, and this comes from, I mean, this is the fact about the largest unramified extension in DVRs in this case, so don't worry, this isn't obvious. All right, so in particular, the map from OL into L, I mean, it's just into its fraction field, gives us a reduction map. So we have a reduction map. R from AL, which by the Neron mapping property, and because n is separated in this case, so the set AL, L rational points, is equal to the set N OL. All right, so remember, by the Neron mapping property, we have a surjection this way, but then it's also an injection because we have separated this with N.
The Neron mapping property says there is a unique extension,
Yeah.
so it automatically gives that it's a bijection.
Okay, yes.
I mean,
yeah.
it's also full of separations.
Yeah, that's right. So we have a reduction map. Right, so we have quality this way, and then
But you still have to do the reduction, right?
oh yes. Yes, and then we get to the special fiber, or to the k bar rational, to the k bar rational points of the special fiber. Surjectivity in this case, it follows because, so we're assuming that R, that R is Henselian. Did I write that in the proof? Okay, so surjectivity follows, so this is a fact. It follows first but by the smoothness of N and the fact that we're working over a DVR. You can lift smooth sections over Henselian.
Isn't OL in fact the strict cancellation of your base DDR?
You have to localize.
Okay.
It is local.
Then I think so.
Yeah.
Okay. And then it is inside.
Sorry.
And then it is inside.
Yes. Okay. Yes. So this follows the surjectivity by, for example, corollary 6.213 of Lu. All right, and we're almost done this part, and I guess we'll have to stop there. So this looks very promising. Yep. Now, what we have is that the kernel of R is in fact uniquely divisible by n. So this is not so obvious, but we'll just take it as a black box for now because it's not. I mean, it's not super relevant to the Neron models part. So it's uniquely divisible. By m. So in particular, it doesn't have any points of torsion order dividing n. All right. So what we get, so this implies that we have a surjective homomorphism from homomorphism. So we get hom z modulo mz AL, which is equal, once again, to AI to the M, onto the set of homomorphisms from Z mod MZ to the k-bar rational points of the special fiber, which is equal to N tilde N. And then because it's uniquely divisible by N, this is in fact a bijection. All right, and this is very good then because we know now that so what this implies is that AI to the M, I mean it's isomorphic to a group. So this is a free Z mod MZ module of rank twice the dimension N tilde, which is twice the dimension of A.